Hello students, welcome to Vista's Learning. This is Shruti Nadiga. We are in 11th standard chemistry and we Vista's Learning give you the quality education for all. Yes students, so whenever we are seeing about the chemistry, we are worried about how difficult is it, right? So yes, this is the very difficult part where we are going into. But if you are using this daily or routine, if you are getting into that, then you have to study this, right? So what we are studying now? Hydrocarbons. Again hydrocarbons. Already we have finished 6th lecturing class and this is the 7th lecturing class. But still we are in the hydrocarbons. And what are these? These are the aromatic compounds. Here we have the benzene and the other substituents where hydrogen will be substituted with the other groups and that will be the benzene derivatives. So about these things we are studying today. Got it? Yes. So we are speaking about the aromatic hydrocarbons. Aroma means odor, smell. So these will be also called as arenes. As we see here, they all have the double bonds. Yes. Since they all have the double bond, they'll get the ENES at the end. So aryl group with double bond will be considered as arenes. What do we call them as? Arenes. And as we know, they have a pleasant smell. These have the pleasant smell. So the odor means smell. Smell will be very good of these and so we call them as aromatic. Aroma means pleasant smell. So these gives you pleasant smell and hence those compounds will be called as aromatic hydrocarbons. But nowadays whatever the derivatives we are having, every derivative of this benzene or the aromatic compounds what we call today will not be having the pleasant smell. But at the initial stage, they were having the primary members were having this pleasant smell and hence got the name as aromatic compounds. The class as named as aromatic compounds because of that smell. Fine. Most of such compounds were found in the where they'll be having the benzene ring. What is the benzene ring? If they have this hexagonal structure and alternative single and double bond, then we call it as benzene ring. So benzene ring is highly unsaturated, but in a majority of reactions, aromatic compounds, the unsaturated benzene ring is retained. That means whenever we are undergoing the reaction, if it is carbon-carbon triple bond or carbon-carbon single double bond, they will react and either it might be the substitution reaction or addition reaction, they react and give you the products. But here these benzene ring if you have, they are stable than that of this alkyl groups. So these are the examples of aromatic hydrocarbons where you cannot or you do not contain a benzene ring, but instead of containing the other highly unsaturated ring, that means these group aromatic hydrocarbons, what we are saying, the benzene group if you have, they are coming under this aromatic. Some doesn't have the benzene group. They have like this. Fine. But even though if they are not having or consisting of benzene ring or benzene group, and still they can be grouped under this aromatic hydrocarbon. For that, we have a rule. So aromatic hydrocarbons contain benzene ring are known as benzenoid, whereas if they don't have that benzene ring in them, then they'll be grouped as non-benzenoid hydrocarbons or aromatic hydrocarbons. Here we have some of the benzene and benzenoids. So what we say, benzene ring, where this is the toluene. If you remove one hydrogen and substitute with the methyl group, we'll get this toluene. And two benzene ring, if it is being clubbed together, we get the naphthalene. Do you remember where do we see this naphthalene? The naphthalene balls. We can speak about this later. This is called as diphenyl. This benzene, if we have the benzene ring like this, it will be C6H6, right? So if you remove one hydrogen and substitute the other one, By removing this, we can call this as phenyl. If you have here, we can call it as this substitution for this, we can call it as phenyl. So diphenyl means two phenyl groups are attached together. So this is one phenyl, that is one phenyl. So two benzene ring which has been attached, we can call them as diphenyl. So nomenclature and isomerism, as we know, whenever we are introducing the compounds, we need to know about their naming. How do we name that? So all 6 hydrogen atoms in benzene are equivalent, and so we can have only one substituted product which is been formed. And when you go with the two hydrogen in hydrocarbons, in the benzene ring, if you have two hydrogen which is been substituted. So if you substitute only one, generally what happens? Only one hydrogen will be substituted. Then we can just call it as methyl benzene, or we can also call it as toluene. Likewise, chlorobenzene, bromobenzene. If it is been substituted with chlorine, chlorobenzene. Remember, we should have alternative single and double bond. So if you have this chlorine, chlorobenzene will say. But if you have two hydrogen which is been linked to this hydrogen or substituted with the hydrogen, then will not get only one type of products, will be having two different types. The benzene ring, I'll just take 3 benzene ring here so that you can understand better. Right. So first one hydrogen will be there. So all will be having one chlorine atom. So they all are called as chlorobenzene. And the second one hydrogen, I can get it either here or here. So both are the same. So I'll keep it here. The third one, I can get it here. And the fourth one here. If I get here, that will be also 1, 2, 3. Third one, right? Then numbering we know. So here what happens, we'll be having 1, 2. So 1, 2 dichlorobenzene. Here 1, 2, 3. Why we are not naming from here 1, 2, 3, 4 it will become, right? 1, 2, 3, 4 and here 5. So 1, 5 will not come. As we know, it should have the substituted carbon should have least numbering. So we'll take 1, 2, 3. So it will be third. 1, 3 dichlorobenzene. And here 1, 2, 3, 4. 1, 2 dichloro, 1, 4 dichlorobenzene. Got it? This in common will take any substitutions either here or here as ortho. If any substitutions are at this point 1, 2, 3, 1, 2, 3, then we call it as meta. If they are exactly opposite to this carbon atom, then this position will be called as para. So generally we can have the first 1, 2 chlorine as, if I have chlorine here and one more here, we can call it as orthochlorobenzene. Okay. The next one will be meta. Here chlorine, here will be having another chlorine, metachlorobenzene. If the same thing, if I have here this one will be called as parachlorobenzene. Fine. So we need to know how to name them. So when two hydrogen atoms in the benzene are replaced by two similar or different monovalent atoms, because we know it will be having only one valency which has been satisfied already with the 3, it requires one more valency. So we want monovalent atom or group of atoms. 3 different positions of isomers are possible, as I said, ortho, meta and para. So 1, 2 or 1, 6 is known as ortho. Likewise, 1, 3 or 1, 5 will be called as meta. Generally, we will not take it as 1, 5, we will take it as 1, 3 or 1, like we'll call it as meta. And 1, 4 will be called as para. So these are the isomers. What isomers? Position isomers. Position isomers for the substituents. Either they can take the position of 1, 3 or 1, 2 or 1, 4. So we'll get ortho, meta and para isomers. You can see we have a toluene here where methyl benzene. One hydrogen will be removed and we have a methyl benzene. The next one, 1, 2. So what do we call it as? 1, 2 dimethyl benzene, or we can simply call it as orthoxylene. This is a common name. Orthoxylene is a common name. Likewise, if it is for 1, 3, we call it as 1, 3 dimethyl benzene, and we can also call it as metaxylene. What we call it as? Metaxylene. Likewise, if you see here 1, 4 dimethyl benzene, this can be called as paraxylene. So what you are understanding here, what do you mean by xylene? If the benzene ring has been substituted with 2 CH3 or methyl group, then it will be called as xylene. And the positions will be given by ortho, para and meta will give you where those substituted methyl group will be positioned or where they are present. So either 1, 2 or 1, 3 or 1, 4. Next, the structure of the benzene. As we know, this has been isolated by Faraday, Michael Faraday in 1825. And the molecular formula of benzene is C6H6, indicates a high degree of unsaturation. That means it will be having 3 double bond where it is been unsaturated. The molecular formula did not account for this relationship to get corresponding alkanes or alkynes. So if you see this C6H6, it is not like, it will be like CnHn, right? So that doesn't have any relationship with alkenes and alkynes, because alkanes will be CnH2n plus 2, whereas alkenes is CnH2n, whereas alkynes is CnH2n minus 2, right? Whereas it is CnHn, or you can take C6H6. So this C6H6 is not having any molecular formula. It is not accounting for any of these 3. So benzene was found to be stable molecule and found to form a triozonide, which indicates that the presence of 3 double bonds. So benzene was further found to produce one and only one mono substituted derivative, which indicated at all the 6 carbon atoms. If you take the benzene ring, they all will have similar hydrogen atom. So what happens? The substitution takes place only with one hydrogen atom, which can be called as they have identical hydrogen atoms, so leads to the mono substitution or mono derivative. This is the structure of benzene, where each carbon atom will be having one single bond with the other carbon atom, and two bonds, double bond with the other adjacent carbon atom, and one single bond with hydrogen. So you can see that one sigma bond with hydrogen and one sigma bond with the either of the side of the carbon atom, and one pi bond. So this is how the carbon will be given in the benzene ring. So you can directly write this as like this. So this gives you the structure of benzene. So Kekule's structure indicates the possibilities of 2 isomeric 1, 2 dibromobenzenes that we'll get to know. In one of the isomers, the bromine atoms are attached to the doubly bond carbon atoms, whereas in the other they will be attached to the singly bond carbon atoms. Here you will be having this bond structure where this is one and this is another one, where the double bond is here for C1, C2, C3, C4, C5, C6. But here the double bond will be, if I am just writing the same carbon atom, 4, 5 and 6. the double bond will be shifted towards this. So what happens? Now, the carbon atom where bromine is attached will be for C1 here, where it is having double bond with carbon 2. Where now I have the Br where it is having the double bond with this. So we have the difference in the structure. Those structures will be coming like this, where if we take the double or double substitutions or two substitutions, they will be connected in such a way that the bond will be single here, where here is double. So does it have any difference in the structures, or does it have any difference exactly? No, because these benzene ring will be having the delocalized pi electrons and they will be having the shifting. So these are the two types where Kekule gave the structure. Kekule structure where they can easily be shifting the or delocalization of pi electrons takes place. And due to that, there is no difference or there is no exact difference between this and the structure. So benzene was found to form only disubstituted products, right? One or two disubstituted product. This problem was overcome by this Kekule by suggesting the concept of oscillating nature of this double bonds. So as I said, the double bonds will be shifting. They will be shifting from one carbon to the other. That was given by this Kekule. Even with this modification, Kekule structures of benzene failed to explain unusual stability and preference to the substitution reaction. That means it should be stable, right? And the preference for the substitution reaction than addition reaction, which could later be explained by the resonance structure. We have this benzene ring. He said this has been delocalizing, right? He gave the oscillating nature of this double bond. This double bond will be oscillating, so will be having this property where it is stable and it is not much stable than that of the resonance structure. If it is stable, then it should not react with the substitution reaction, or else it should not give the addition reactions. But it is giving substitution and addition reaction. Why? Because the resonance structure matters here, and the reaction, how it takes place, will explain in the next sessions. So this is how the benzene ring will be having its oscillatory double bond or pi bonds. So as they are shifting, what happens? This Kekule gave this suggestion that the pi bonds will be shifting and hence the reaction will be, or they are stable. But he cannot explain with even with this structures that why they undergo the reaction. After getting the substitution and addition reaction, they are stable. Why? So according to valence bond theory, the concept of oscillating bond in the benzene is now explained by resonance. So it will be given by the resonance. Benzene is a hybrid of various resonating structures. As it will be keep on moving, it has a various resonating structures, and two structures are given as we saw here. These are the structure A and structure B, which are stable, and it is been given by Kekule, and we can say them as the resonance structure of benzene. The hybrid structure is represented by inserting a circle or a dotted circle in a hexagonal or hexagon, what we say it as the benzene. Okay, so we can say that if this is a hexagon, and here we can put the dotted structure to show that the double bond is been oscillating, or we can directly just put a single circle like this. That will give you the resonance structure or the hybrid structure of this benzene. So the circle represents the 6 electrons which are delocalized between the 6 carbon atoms of the benzene ring. As we know, they will be having the 6 carbon atoms, and for each carbon atom we have the pi bonds, and that will be oscillating. The orbital overlapping gives us better picture of this structure of benzene. We'll see through that. And as we know, this carbon will be having sp2 hybrid orbitals. So what happens? It will be having sp2 hybrid orbitals and one p bond. This p orbital will combine with the adjacent carbon atom by this to form pi bond. So remember, one sigma bond and the one pi bond will be present in between adjacent carbon atoms, as it is having the sp2 hybridized carbon atoms. So two sp2 hybrid orbitals of each carbon atom overlap with sp2 hybrid orbitals with the adjacent carbon atoms to form 6 carbon-carbon sigma bonds, which form the hexagonal plane. So this is one bond what I have shown you. If we see each carbon atom, so each will be having sp2 hybrid orbitals. So they will be overlapping like this. So what happens? Each will be having sp2 hybrid orbitals. Each carbon atom will have one sigma bond between each carbon atoms, right? And they have one more orbital which the hydrogen will be bonding with this sp2 hybrid orbitals, where hydrogen also makes the sigma bond with this sp2 hybrid orbitals, right? And they all will have one pi bond. As we know, they all will be having one pi bond, and they overlap each other with the adjacent carbon atoms to get this benzene ring. So this is how the benzene ring is been formed. So remaining sp2 hybrid orbitals of each carbon atom overlap with the s orbital of a hydrogen atom to form hydrogen and carbon sigma bond. Each carbon atom is now left with one unhybridized p orbital perpendicular to the plane. Perpendicular to the plane means if we are having this bond like this. So this is a plane. I'll just write it over here like this. This is a plane. They are perpendicular to this. If I have a plane here, the benzene ring is here, the plane exactly perpendicular to this will be having the p orbital. So lobe will be on, one lobe will be upper and other will be like this at the down. So they will overlap. If I say like this, they will be perpendicular to the plane and they will overlap laterally to form pi bond. Hope you are getting this point. So this is how you can see each p orbital will be perpendicular to the plane, right? You will be having these white lines what I am showing. They are the sigma bond between each carbon atom and will be having one bond with hydrogen atom, this, okay? So that hydrogen atom, that will be also sigma bond, and these will overlap like this laterally. So these overlap laterally and gets the double bond or pi bond. So the unhybridized p orbitals of carbon atoms are close enough to form pi bond by lateral overlapping. There are two equal possibilities to form 3 pi bonds by overlapping of p orbital. So if we take this C1, C2, C3 C4, C5 and C6, the double bond or the pi bond can be between C1 and C2, or else it can be on the other side. If I write the C6, C5, C4, C3, C2, now the bond can be overlapping via two methods, right? Either C1, C2. Now, or else these can be overlapping like this. So, if these two are overlapping, then these two will get overlapped and this will be overlapped like this. This is one type, and the other type is that they will be overlapping for C1 and C6. So, these will be overlapping like this, and hence these get overlapped in this manner. Getting? So, we have C1, C2, C3, C4 and C5, C6, or C2, C3. C2, C3 is this. C2, C3, C4, C5 and C1 and C6, as you can see here. So, here again you can see these two, these two, these two. So, which gives you the structure C1, C2, C3, C4, C5 and C6. So, here in between C6 and C1 we have double bond, C5 and C4, C3 and C2. Getting? So, this is one structure. And as we saw that two calculus structures with delocalization of pi bonds, we have one more where here the bond will be like this. So, you can get this will be C1, C2, C3, C4, C5 and C6. So, now the double bond is in between C1 and C2, C1 and C2, C3 and C4, C6 and C5. So, respectively we have that bond. Good. The intermolecular distance between all the carbon atoms in the ring has been determined by the X-ray diffraction to be the same. That means they all are same by X-ray diffraction method. We can see that all the carbon atoms are of equidistance from each other. There is an equal probability for the p orbital of each carbon atom to overlap with the p orbital of the adjacent carbon atom. Either they can go with the one, C1 can go with C2 or C5, C6. Either of the side it can, and they have an equal probability of doing so. And hence we get this ring where the pi bond will be present and we have the electron cloud above and below the plane. The 6 pi electrons are thus delocalized and can move freely about 6 carbon nuclei instead of only 2. That means they can easily move all over the 6 carbon atoms. They can easily move through the 6 carbon atoms instead fixed to only 2 carbon atoms. The delocalized pi electron cloud is attracted more strongly by the nuclei of the carbon atoms than that of the electron cloud localized between two carbon atoms. Means if you have the delocalized pi electrons, they are attracted more strongly by the nuclei of the carbon than that of the electron cloud of the localized carbon atom. The presence of delocalized pi electrons in benzene makes it more stable than that of the hypothetical cyclohexatriene. That means if you have this delocalized pi electrons, they are stable than that of this having only one type of structure without delocalization. Why they are stable? Because they have the resonance structure. So, X-ray diffraction data reveals that the benzene is a planar molecule. Had any one of the above structures of the benzene been correct, two types of carbon-carbon single bond length were expected. Means it might be having any of the difference in that, but X-ray data indicates that all the carbon-carbon sigma bond or single bond length are the same of order 139 picometer, which is intermediate between the carbon-carbon single bond and the carbon-carbon double bond. That means, as we know, carbon-carbon single bond will be having 154 picometer, whereas double bond will be having 133 picometer. But here for the benzene-benzene carbon-carbon bond, either it is not a single bond, because if it is a single bond, it should be 154 picometer, or else it is not double bond. If it is double bond, it should be 133 picometer. It is in between. That means it will be having 139 picometer. Each carbon atom has this 139 picometer. That means the delocalization of the electrons are responsible for this. Thus, the absence of pure double bond in benzene accounts for the reluctance of benzene to show that addition reaction under normal conditions. So, since we have this, it is not having fixed double bond. It have the fluctuation, or in between single and double bond, we have this, and hence that gives you the property of benzene to react with addition, to form the addition reaction. Next, what do you mean by aromaticity? So, this aromaticity will be given by some rule, where we have the Huckel rule to say about this. Benzene was considered as parent aromatic compound. Now, the name has been applied to all the ring system, whether they are aromatic or not. Either they are benzenoid or not, either they contain benzene or not. So, they will be given as the aromatic compounds. So, these aromaticity will be given by certain properties. They should be containing a plane structure. So, planarity should be maintained. As we say, benzene is a plane structure. So, it is a plane structure, so we can consider it as it is having the aromaticity, but some will be not in the plane. They will be different. For example, they will be like this. The structure will be there. They will be like this. They will be not in single plane. Then what happens? We cannot call them as aromatic compounds, or they doesn't give the property of aromaticity. Complete delocalization of pi electrons in the ring. They should have this moment of delocalization of pi electrons. And one important thing what we need to remember is this: the presence of 4n plus 2 pi electrons. What do you mean by n here? N is the ring. As we know, these aromatic compounds are containing the ring structure, right? So, they should have one ring. If you have one ring, then this should be like 4n plus 2 pi electrons should be present. That means you should check that the pi electrons are there or not. If there is no pi electrons, then it will not be considered as aromatic. And one thing, that should be containing one ring. So, if it is containing one ring, then what happens? How many pi electrons will get? We need to substitute. N is equals to 1. 4 plus 2 is 6 pi electrons. So, as we see the benzene ring, if you see, this is having one ring, right? And n is equals to 1, if we substitute, we'll get 6 pi electrons. 6 means 1, 2, 3, 4, 5, 6. So, each double bond will have 2 electrons, pi or delocalized electrons. So, each bond can be considered as 2 electrons, and 2 3s are 6. So, this benzene have 6 pi electrons. We are not considering about the sigma bonds here, only the double bond or the pi bonds we are considering. So, we'll get 6 pi electrons, which is been satisfied by benzene. If it is satisfied by like this 4n plus 2 rule, then we can consider them as aromatic, or they are possessing the property aromaticity. So, this is often referred to as Huckel's rule. What do we call it as? What is Huckel rule? That is, Huckel rule says that if a compound should be aromatic, or it should possess aromaticity, then it should obey this 4n plus 2 pi electrons rule. So we'll see here, we have a benzene ring here. We have cyclopentadienyl anion. So here what happens is that we have one single bond, right? So we have 4n plus 2 pi electrons, right? N is equals to 1 here. So it should contain totally 6 electrons, pi electrons. Here we have two bonds, two double bonds. So two double bonds will give you 2 plus 2, 4 pi electrons. And you can see here one negative charge. One negative charge implies 1 plus 1, 2 electrons. So that means 6 electrons are present, and these electrons can also be used in resonance. They can also be delocalized, and hence we can call it as it is uh, it is giving us the aromaticity, and it is holding good for Huckel's rule. If you see this cyclohepta, hepta means 7 carbon atoms are there. Hepta, tri-enyl, 3 double bond. So enyl means you will be having that group name, and cation for positively charged. So the cyclohepta tri-enyl cation, if you see this positive charge will not give any electrons. So 6 electrons are there for one single ring. So this also will be considered as the aromatic compound. The naphthalene now. Naphthalene, if you see 1 plus 1, 2 rings are there. So if you go with this rule, 4 2s are 8, 8 plus 2, 10. So how many bonds are there? 1, 2, 3, 4, 5. So 5 into 2, that is 10. So even naphthalene will be called as aromatic compound, or it exhibits aromaticity according to the Huckel's rule. Next we have anthracene, 3 bonds. So 4 3s are 12, 12 plus 2, 14. So it should have 14 pi electrons. 1, 2, 3, 4, 5, 6, 7. 7 2s are 14. Yes, it will be having 14 pi electrons, which says that the anthracene is also exhibiting the aromaticity. Phenanthracene, see, it will be having a linear one, where here it will be having the position will be changed. So even here what happens? 1, 2, 3, 4, 5, 6, 7. So 3 ring with 7, 7 2s are 14, 14 pi electrons. So these all will come under aromaticity, or they all come under aromatic compounds. Is it clear? Good. Preparation of benzene. As we got to know the properties now, we'll go ahead with the preparation of benzene. How to prepare this benzene? The first thing, benzene is commercially isolated from the coal tar. However, it can be prepared with the laboratory process also. We know this process, cyclopolymerization of ethine. Last class, we have learnt about this, right? We have ethine, right? With triple bond. So what happens here is that they undergo polymerization by shifting of the bonds, and we get benzene ring. Single bond, double bond, single bond, double bond, single bond, double bond. We did it in the ethine, right? Do you remember? Good. What is the next one? Decarboxylation of aromatic acids. The aromatic acids, if you remove the aromatic acids, generally carboxylic acids will be having COOH with R group. If you remove this COO, then what happens? CO2, that is carbon dioxide. D means to remove. Carboxylation, to remove this carboxylation, carbon dioxide. Then this hydrogen will be attached to this R. Hence we can get the aromatic benzene from the aromatic acids. So here you can see sodium salt is being used such that the hydrogen which is present with this acid, carboxylic acid, hydrogen will be removed and sodium will be added. Sodium salt of this will be treated with sodium hydroxide, where in presence of calcium oxide at a particular temperature or giving certain heat energy or on heating with soda lime, will get benzene which is been formed, and removal of this Na, this sodium will go with this sodium carbonate to form the sodium carbonate. So you can see here Na2, one carbon atom, and oxygen will go from here, will get CO3. So one benzene ring which is been formed, and hydrogen. So what happens here? This will go to give Na2CO3, and this hydrogen will be attached here, forming benzene with sodium carbonate. Next, reduction of phenol. Phenol is the structure where it is like benzene, but hydrogen is being substituted by OH group, hydroxyl group. So this structure will be called as phenol. So from phenol we can get the benzene ring. So we have to reduce the phenol. Reduce the phenol means add the hydrogen, remove the OH group. So phenol is reduced to form the benzene by passing its vapor over the zinc dust. So what happens? We have OH group, and that will be removed easily. The hydrogen, oxygen can be removed easily by zinc, forming benzene. Hydrogen will attach back to this such that we get this reaction with the formation of benzene and zinc oxide. Next, coming with the physical properties, as we know, the name suggests it will be having the pleasant odor. So aromatic hydrocarbons are non-polar molecules and are usually colorless liquids or solids with the characteristic aroma. Aroma means smell. Naphthalene balls, you might have seen this, right? Naphthalene balls will use in almaras, even in washrooms and all, so that you can see those are the naphthalene balls which we are using in toilets and for preservations of clothes because of unique smell of the compound and moth repellent property. So it has its own smell such that it will repel the moths or insects. So aromatic hydrocarbons are immiscible. That means they are not soluble with water, but they are readily miscible with organic compounds. Why? Because these are non-polar. They are non-polar, whereas water is a polar molecule, and hence the polar gets dissolved, whereas non-polar polar will not be miscible. Since they both are liquids, they are immiscible. So they burn with sooty smell, giving you carbon dioxide or carbon monoxide or carbon. So these are the physical properties. Now we are going ahead with the chemical properties. What are the chemical properties? How do they react with the other substances? So arenes are characterized by electrophilic substitution reactions. Electrophilic substitution reactions means electrophile will be substituted. So electro means the rich in electrons. Philic means attracted towards. The one which is being attracted towards the electrons or negatively charged particles will be called as electrophiles, and the reaction where they are being substituted will be called as electrophilic substitution reaction. However, under special conditions, they can also undergo addition and oxidation reactions. We'll go ahead with this electrophilic substitution reactions. So we will be having more number of such reactions. The common electrophilic substitution reactions of arenes are nitration, halogenation. Nitration means addition of nitrates, halogenation, addition of halogen, sulfonation. When the benzene is been reacted with sulfuric acid, we'll get this sulfonic group which is been attached to the benzene ring, forming sulfonation. And Friedel-Crafts alkylation, that means alkyl group is attached, and acylation where CO and RCO group will be attached. So these are acting reagents. As we say, it is an electrophile. So if you have negatively charged particle, this will get attracted soon. It is been attracted by the negatively charged particle. So it should be positively charged, and hence we can substitute it with, or we can give the representation as E plus, electrophile. So it is attracting the negative charge. That means if it is been attracted by the negative charge, or it is attracting the negative charge, it should be positively charged particle. So we'll get into this nitration. So nitro group is introduced into the benzene ring when benzene is heated with the mixture of concentrated nitric acid as well as sulfuric acid. So we call it as nitrating mixture. If you mix both and add it with the benzene, we get the reaction like this, where benzene is being treated with nitric acid and sulfuric acid to get the substitution of nitro group to the benzene ring. That means hydrogen will be removed, NO2 will be added. As we know, HNO3, NO2 will come here. So OH will be remaining. So one hydrogen will go with that, forming the water molecule, and that place of hydrogen will be taken by the nitro group. So we get nitrobenzene here. Next we have halogenation, where arenes react with halogens in presence of Lewis acids like anhydrous aluminum chloride or iron chloride or iron bromide to yield the haloarenes. So we have benzene in presence of chlorine. We have anhydrous aluminum chloride, where we get one hydrogen removed with the chlorine to form HCl, and we get chlorine which has been taking place with the hydrogen. So we get the chlorobenzene. This is the substitution reaction where halogen has been added. So we call it as halogenation. Next, sulfonation, the replacement of one hydrogen atom by the sulfonic group in a ring is called as sulfonation. It is carried out by heating benzene with fuming sulfuric acid. So if you see the sulfuric acid, fuming means it is very concentrated sulfuric acid. So when we are treating this benzene with this sulfuric acid, HSO3 will be attacking here, forming benzene sulfonic acid. Next, we have the Friedel-Crafts alkylation reaction. This is important even for your second year or 12th standard. As we know, this Friedel-Crafts will come under naming reaction. That you should remember, much more important question. Friedel-Crafts alkylation, and you have Friedel-Crafts acylation. Even this will be there for the nitration, sulfonation, and halogenation will be there for 12th standard. This is for nucleophilic substitution. There in 12th you will be having nucleophilic substitution reaction. This is for electrophilic substitution. So as we see, when benzene is treated with the alkyl halide in presence of anhydrous aluminum chloride, alkyl benzene is being formed. So if you take the benzene which is been treated with ethyl chloride in presence of anhydrous aluminum chloride, so what happens? This one hydrogen will go with this chlorine. So R group will be attached with this carbon atom, hence giving ethyl benzene with HCl. So you can also have one more example where methyl chloride is been taken. So benzene reacting with methyl chloride, HCl will be removed out, and chlorine methyl group will go and take the place of hydrogen in presence of aluminum, anhydrous aluminum chloride, and we get the toluene or methyl benzene. Next we have acylation reaction. The reaction of benzene with an acyl halide or acid anhydride in presence of Lewis acid, that is aluminum chloride, will give you this acyl benzene. So this is the acyl group. Acyl group will be RCOCl. This is acyl chloride, right? So here what happens? If you remove this chlorine and this group is attached to the carbon atom COCH3. So R is CH3 here. Then we call it as acyl benzene. So this is how we get benzene reacting with acetyl chloride in presence of anhydrous aluminum chloride. Why? Because it is a Lewis acid. So that mechanism we'll study in the next session. So we'll get acetophenone with removal of hydrogen chloride. Similarly, if you are taking acetic anhydride, so what happens? COCH3 will get with removal of CH3 COOH group. So in presence of aluminium, anhydrous aluminium chloride, benzene reacts with acetic anhydride to give you the phenyl acetophenone with acetic acid. This how the reaction takes place mechanism we'll study in the next session. If excess of electrophilic reagent is used, further substitution may take place in which other hydrogen atoms of benzene may also be successively replaced by the electrophile. Now we are just using the limited reagent so that only one hydrogen is replaced. If we have more number of hydrogen atoms, more number of reagents or more amount of reagent present in the system, what happens? That also undergoes substituting the other hydrogen atoms in the benzene ring. Hence, as we know, ortho, meta, para substitutions will be formed. So, for example, benzene on treating with the excess of chlorine in presence of anhydrous aluminium chloride can be chlorinated in such a way that all the hydrogen can be removed, forming hexachlorobenzene, and hence it can be given by the formula C6Cl6. So, benzene treating with the chlorine in presence of anhydrous aluminium chloride, it is taking place in the dark and cool place. When this reaction is been taking place, you get the product where each hydrogen is been removed by the other chlorine atom to form hydrogen chloride or hydrochloric acid, and all the other chlorine will be attached with this benzene, forming hexachlorobenzene. Got it? So, this is how the addition of halogen takes place, and you can just go through this all reactions, and we have the mechanism how does these reactions will take place. Electrophilic substitution reaction mechanism we have, that we'll study in the next session. So by the next session, we'll finish our hydrocarbon topic, students. Hope you enjoyed our class. If you have any doubts, you can get back to us. As we Vistas Learning have all our efforts before you, so that we want to help you out with the studies. If you have any doubts regarding any of the topics, you can get back to us in our web application www.v-learning.in. Thanks for watching Vistas Learning.